All right. Hello, senior math. Today we are continuing talking about our arrangements of items and how we can arrange different things. We'll talk a little bit how this relates into probability, what we just talked about as well a little bit today. So yesterday we talked to, or not yesterday, last Friday, no, Tuesday, I apologize. Tuesday we talked about permutations, which was how we could arrange different items where order was important. Today we're going to talk about combinations, which is essentially arranging items where order is not important. But to help us review our permutations today, you had this warm up as your at the start of your class. So let's go over this warm up together. So we said from your class of 13 students that are in this senior math class, you need to choose a president, a vice president, and a secretary. How many possible permutations are there? So if we remember that permutations, you have your total number and then you have how many you're choosing. And we use that NPR, that number permutation choice, to represent our permutation. We could use this using our Desmos calculator. So all we had to do was we knew our number of total students was 13 total possibilities to choose from. We're doing a permutation because order is important because it matters which student is president, which student's vice president, which student's secretary. That makes a difference. And then we're only choosing 3 because we're choosing president, vice president, and secretary. So 13 permutation 3, we're going to plug this into our calculator and we're going to see what we get. So pulling up our Desmos, went to functions, we went to stats, and then we went to NPR, and we did 13, 3, and that gave us a total of 1,716 possible permutations. So just within this 13 class, just choosing 3 people as president, vice president, and secretary, there's 1,716 possibilities of different combinations, which seems like a lot for just a small class like this, let alone an entire grade or something. All right, so what if order didn't matter? For example, if ABC is the same as CBA because it uses the same 3 letters. So if order does not matter, this is called a combination. So once again, ABC, because it uses the exact same letters as CBA, those would be the same combination, but they would be different permutations. We use combinations when it's not important which ones are chosen. Everything is the same. So for example, in that last example, we talked about vice president, president, and secretary. Those are 3 different positions. But if we're just choosing 3 people to fill 3 of the same positions, let's say 3 people are on doing all of the same job, you just need 3 people, it's going to be different because it doesn't matter which one's president, it doesn't matter which one's vice president, it doesn't matter which one's secretary, it just matters that they're all 3 who have been chosen. So when order does not matter, this is called combinations. And we use the same way of calculating permutation, it's just the formula is slightly different. So we do NCR, which is typically said as number something choose R is another way of seeing it, or number combination R. We take the number of values, the number of options factorial, that's still going to be in your numerator, and then we're still going to divide by n minus r factorial, just like permutation. The one thing that's different, though, is that we add on this r factorial. So you're also dividing by the number chosen factorial again. And the reason we're dividing by that again is because that's going to represent how many duplicates we have. Because if in permutations, ABC and CBA are different things, but in combinations, they're the same. So we need to make sure we cancel out all those duplicates so that we don't get those happening again. So that's what that R factorial represents. Those are our duplicates. So we have to divide by those duplicates. So for example, if you had 6 things and you're choosing 4 of them, seeing our combinations, we would do 6 factorial divided by 6 minus 4 factorial times 4 factorial. And that would be our value. So we know 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. 6 minus 2 factorial, or 6 minus 4 factorial is just going to give us 2 factorial. And then 4 factorial is 4 factorial. So this is really 6 times 5 times 4 times 3 times 2 times 1, all divided by 2 times 1 times 4 times 3 times 2 times 1. Well, if I have 4 times 3 times 2 times 1 in my numerator and 4 times 3 times 2 times 1 in my denominator, those are going to cancel out because anything in my numerator multiplied, anything in my denominator multiplied. Those can cancel out. So really, I have 6 times 5 divided by 2 times 1, which is just 30 over 2, which gives me an answer of 15. So 6 choose 4 is going to give me 15. Once again, we could also put that into our calculator, our Desmos calculator. Pulling up Desmos, if we go down, just with that same functions, under stats, right next to NPR, we have NCR. So we're going to do that the exact same way. We're going to do 6, 4, and we get our answer of 15. So once again, using that Desmos calculator is going to save us so much time because we don't have to use that formula, which takes a lot more work to have to work through. So the question is, are there more combinations or less combinations than permutations? And the answer to this is there's always going to be less. There's always going to be less combinations. The reason there's less combinations is because we're not counting duplicates. So we said we are dividing by those duplicates, so we're not having those extras show up. So A, B, C, and CBA are not showing up, so there's going to be less options to choose from because those represented the same thing. So without having those duplicates, combinations will always give you less numbers than permutations will. So combinations will always give you smaller answers. So how many different ways can a 2-person committee be chosen from 8 people? So this is a combination because it doesn't matter which order I choose the 2 people because they're both going to be doing the same job. They're on a 2-person committee. They're doing the same job. So it doesn't matter which order I choose them, whether I choose this person first or that person first. As long as both those people are chosen, that is a combination. So we are doing 8 choose 2, and that is going to be our combination. Out of 8 total people, we're choosing 2 of them. So pulling up Desmos, I'm just going to change this to 8, and then I'm choosing 4 people, or sorry, I'm choosing 2 people. So we get 8 choose 2 gives us 28 total options. So out of 8 people choosing 2 for my committee, I have 28 potential different committees that might show up out of those 2 people from those 8. So we're having a random drawing to see which 3 students in our senior math class get a free subscription to the Jelly of the Month Club. How many possible combinations are there? Well, once again, we said earlier today that there are 13 total students in our class. It doesn't matter which order I choose the 3 students. So this is going to be a combination because all 3 students are getting the exact same thing. They're all getting the same subscription to the Jelly of the Month Club. You know, big bucks right there. So we're going to do 13 choose 3. And we'll actually see how different this is versus our permutation that we did at the very beginning of class. So we're going to do functions and choose R, 13, 3, and we get 286. So we can actually see there's a large difference from 13P3 versus 13C3 because permutations got us 1,716 versus our combinations, which only got us 286 different combinations. So what is the probability that Caitlin, Jaden, and AJ are selected for this combination? So what is the probability that those 3 specific students are the ones that get access to or get their Jelly of the Month subscription? Well, if we think about it, that's one possible combination. That's one specific combination out of all of my 286 different combinations that I just mentioned. So our probability of getting Caitlin, Jaden, and AJ would be 1 out of 286. That would be our probability. Our desired outcome is that one combination out of our total possible number of outcomes of 286. So we could put that in our calculator. 1 divided by 286 gives me 0.00349. So rounding that is 0.003, which is roughly 0.3%. So it's very, very unlikely that I could guess specifically which 3 students would get the subscription. Because once again, there's 286 different combinations. It's unlikely that I'm going to choose the exact 3 students that are going to give the subscription. But we can use combinations with probability because if we know the desired outcome and we know the total possible outcomes we can get, we can use combinations to help us determine that total outcome for probability, which is handy. All right, how many ways can a 6-person neighborhood crime watch committee be selected if there are 12 men and 8 women applying? Now, nothing in our problem says anything about this Crime Watch committee needing a certain number of men or a certain number of women. So with this question, the 12 men and the 12 women, that's pretty much extraneous information, because this together, we just know that there's 20 people we're choosing from, because we don't need a certain number of men, we don't need a certain number of women. So technically we have 20 total that we're choosing from. So this is really just 20 choose 6. Once again, everyone's going to be on the same committee. Everyone's going to be on the same Crime Watch. So it doesn't matter which order I choose them in, as long as they're all chosen. So we'll go to our calculator. We'll do our function 20, 6. Out of our 20 people, we're choosing 6. That's going to give us 38,760 different combinations. So that's our total number of combinations for our Crime Watch, if out of our 6 people chosen out of the 20. Now, once again, it could be 6 women that are chosen. It could be 6 men that could be chosen. It could be 1 man and 5 women. It doesn't matter. It doesn't necessarily say. So that 12 men and 8 women just really need to be 20 total people, because that does make a difference. A radio station will randomly select 22 postcards from their listeners who enter into a monthly contest. From those selected, 22, along with their original prize, 4 will receive backstage passes into a concert. In how many different ways can the pass winners be selected? So all of these people send in postcards. The radio station selects 22 of them, gives out prizes to those 22, and then from those 22, they're going to give out 4 backstage passes to those specific 22 people, but only to 4 of them. So out of the 22 total, how many or what possible combinations are there that are going to win those 4 backstage passes? Well, it's just going to be 22 combination 4, which once again, we can easily put into our calculator. I'm just going to redo this one. So I'm going to get rid of that 2, put another 2 there, get rid of my 6, put a 4 there. So it's 22, choose 4. And this gives me 7,318. 22, choose 4. 7,318, I believe, was my number. 15, I apologize. 20,315 is my answer. So that's our total number of combinations for pass winners. So let's say 4 friends all have their postcards chosen for their minor prize. What is the probability that all 4 of them are chosen again for the backstage prize, the backstage passes? Well, that's one possibility. That's one combination of 4 friends out of our total combination is 7,315. So once again, our probability that those 4 friends get chosen is going to be 1 out of 7,315. So if we put that in the calculator, we're going to get a small value. I'll just change this. I'll just change my denominator to, that's 1 divided by 7,315, and we get 0.00001. Which is roughly 0.01%. So less than, that's like 1/100th of a percent. That's a very, very, very slim chance that they're all going to be chosen. So unlikely. And then once again, you have to have all 4 of your friends get chosen for the first prize of those 22 postcards out of however many people, and then get chosen again out of those 4. It's very, very unlikely it's gonna win, but it's possible. So you never know. You're telling me there's a chance. There's always a chance, but it's unlikely. So we can use combinations once again. So we're going to look at one last question, and that's where we'll end it for today. The immigration test to become a U.S. citizen is 10 questions that are randomly picked from 100 total questions. How many different combinations of questions can the test be? So we have a total of 100 questions that are random, that can be chosen from. You're only given 10 questions. Now, it doesn't matter which order these questions come in again. So once again, it's a combination because order is not important, but it does matter which 10 are selected. So we're going to do 100, choose 10, and we're going to see how many total combinations there's a possibility for a U.S. immigrant to take. So 100 questions. Nope, sorry, I need to hit my button first. Functions, C, choose R, 100, 10. And that gives us 1.7310 times 10 to the 13th. So this is essentially 1.73 with 11 zeros after it. Which I believe is, nope, I messed up. I believe it's in the trillions. I think it's 17. Let's see, 3. I messed that one up too. So there's hundreds, thousands, millions, billions. So 17 trillion possible combinations. That's how many possible questions or possible different tests can be made out of 100 questions if you're taking 10 question tests each. If you're randomly selecting all those 10 questions, there's 17 trillion different combinations, which is insane. That's a very large number, very, very, very large number, total different tests. All right, that's where we're going to end it for today. You're going to have a little bit of practice over combinations today with a little bit of probability thrown in there. Let me know if you have any questions, and I can gladly help you to the best of my ability. Have a great rest of your day.